Okay, welcome back. Like I said before, I'm just going to use some of this time here to kind of continue lecturing where we left off, and then obviously this will be posted with our others as well. All right, so we left off basically talking about the oxidations of alcohols. And remember that the oxidation sort of reaction that we're talking about, or we're talking about at the end of the last lecture, was basically the idea of removing two hydrogens. And again, the hydrogens are always removed, as we saw, one hydrogen from the OH group and the other hydrogen from the carbon that's attached to the OH group. And then you simply just insert a double bond between the carbon and the oxygen. And that will typically give you either an aldehyde if you oxidize a primary alcohol, or it'll give you a ketone if you oxidize a secondary alcohol. Again, the tertiary alcohol, as we saw there at the end, will not go through oxidation because it's really missing that extra hydrogen that's necessary, a carbon hydrogen bond that's not really there, and it will not give you any type of reaction. So that sort of wraps up our alcohol sort of conversation. We're now going to move on to the next sort of organic group, which are ethers. And again, the functional group for ethers is that carbon, oxygen, carbon run. So again, basically two carbons with an oxygen in the middle is basically the functional group for an ether. And an ether typically will have two alkyl groups on either side of the oxygen. And because of it, it typically has the bent or V-shaped geometry, as we can see here, because these oxygens will typically have our non-bonding electrons. We basically have 4 electron pairs and 2 bonds, and that gives us our bent, our V-shaped, are 109.5 degrees Celsius in terms of the bond angle. So much like water, these ethers will typically have that bent or V-shaped sort of geometry associated with them. Now, in terms of ethers, you do need to know the functional group. So again, that's carbon, oxygen, carbon. When we talk about ethers, we're actually you'll only be responsible for sort of the common name for ethers. So you'll only be responsible really for the common name, not really the IUPAC name. The IUPAC name is a little bit different, so we won't worry about it. So when we name an ether in terms of common way of naming it, it's actually a fairly simple process. You pretty much go to the oxygen and you go to the right of the oxygen and find the group that's there. That's a methyl group. You go to the left of the oxygen and find the group that's there. That's also a methyl group. And obviously, like anything else that we name, when you have two groups in the same compound, that's why we use dimethyl. And then you just simply put ether at the end. So the common way of naming ether is pretty simple. You find the oxygen, you go right, you go left, and then you put the groups in alphabetical order. So you would want to put them in alphabetical order if there was sort of a difference. And then you just simply put ether at the end of it. So let's take a look here. As we can see with these names here. So if we look at our ether over here, we recognize it as an ether. We have a carbon, oxygen, carbon situation. So that's an ether. So again, we simply go to the oxygen. To the right-hand side, we have an ethyl group. To the left-hand side, we have a methyl group. Alphabetical ethyl comes first. So this would be ethyl, methyl, and then again, you just simply put ether at the end of it. Same thing if we come over here. We have a carbon, oxygen, carbon. Ethyl group to the right, ethyl group to the left. So that's going to give us a diethyl. And again, we just put the ether at the end of it in sort of the common way of naming. This is not the IUPAC way of naming. The IUPAC way of naming is, for example, this would be known as methoxyethane, is the IUPAC way of sort of naming. And the way you would name that is smaller group, which is a methyl group, gets the oxy at the end of it. So methoxy instead of methyl. And then 2-carbon group is the ethane part. So obviously for us, the common name will be sufficient, but technically that is the IUPAC way of naming it, which you do not have to know for our class. Any questions on that? Okay. Now, when we look at an ether, as I mentioned, it is a polar molecule, very much like water, which is also bent because it's one of those unsymmetrical geometries. So it is going to be a polar molecule. Now, because it's polar, it could do some dipole-dipole interaction, but it cannot hydrogen bond. So this cannot hydrogen bond. A, because it doesn't have a hydrogen, right, connected to like an oxygen or something like that. But it is polar, so it can still do some dipole-dipole interaction. And if you remember, dipole-dipole is kind of the second strongest. So in terms of things like boiling points, for example, we do find ethers lower than alcohols. Remember, as we talked about today, alcohols, because of that OH group, has the ability to hydrogen bond, right? And again, that's very strong in alcohols. And again, because it has that ability to hydrogen bond, alcohols here will still have the highest boiling point. Ethers would then be underneath them because although they can't hydrogen bond, they can still sort of interact sort of with a hydrogen that's from something else like water. And they typically will have a little bit lower boiling point, but they will have a higher boiling point than alkanes. Again, alkanes, which again are our carbon-carbons, nothing else really there. Our carbons to carbons to hydrogens, our alkanes. They're going to again have the lowest in terms of boiling points because they are going to be using dispersion forces, which are those relatively weak forces. So in terms of boiling points, our alcohol would be the highest, our ether would be next, and our alkanes would have the lowest boiling points, again, because of those intermolecular forces. So as I just mentioned, that's sort of where they fall. Again, they're a little bit stronger in terms of those intermolecular forces than alkanes, which relates to higher boiling points and melting points, but they are weaker in terms of intermolecular forces than alcohols. So you do sort of find themselves in the middle. As this little graph here shows, on the far left, this is our alkane, right? All carbons and hydrogen single bonds. This is our ether. Again, we have the oxygen there. Left-hand side, methyl. Right-hand side, ethyl. Again, ethyl, methyl, ether. And here's our alcohol, which has the ability to hydrogen bond. So this guy with the ability to hydrogen bond, as you can see, highest in boiling point. Dispersion force guy. Weakest sort of force, lowest in boiling point. And then again, our ether here, which again can do some dipole-dipole interaction, sort of in the middle of those two in terms of boiling points. Ethers are also soluble in organic solvents, but kind of like alcohols, if you have not a lot of carbons on it, the ether will be soluble in water. So an important distinction when we talk about hydrogen bonding and sort of boiling points is just to make sure it's clear. When we talk about boiling points and something like hydrogen bonding, what we're talking about is, for example, the alcohol, say methanol, and methanol hydrogen bonding to itself. And then we would break that and it would be at its boiling point to go into, say, the gas phase. Now, when we have something like an ether over here, even though it is technically does not have the ability to hydrogen bond with itself, because it's polar, the oxygen side is more negative, this side is more positive. So when something like water, which is polar, comes along, which is also negative and positive, although the ether cannot hydrogen bond with itself, it does have the ability to interact with something like water and actually make a hydrogen bond between the ether and the water. And that's what's going to allow these ethers that have a lower number of carbons be soluble in water, because it has a way to interact well with it. But just like anything else that's organic, if you build out sort of the ether and you end up with an ether that has a lot of carbons and then like a lot of other carbons, every time you sort of do that, you just make the non-polar side, where all the carbons and the hydrogens would be, much, much bigger. And that little part that is still polar is very small and sort of hidden, and the solubility starts to decrease a lot. So as you can see on the bottom of the screen, as soon as you sort of cross over into 6 carbons or more, the solubility pretty much is non-existent for ethers. But again, upwards of about 5 carbons or less, they will still be able to interact fairly well with water and be soluble in it. Again, because they're able to hydrogen bond, not with themselves, but they're able to hydrogen bond with water. And that helps it be soluble. Any questions on that there? Ethers are also used as sort of anesthetics and kind of put you to sleep and all that good stuff. Variations on ethers nowadays is they take out some of those hydrogens and kind of replace them with some fluorines. Sort of helps with some reactions that people get. But yeah, usually, they kind of will put you to sleep a little bit. Especially diethyl ether was the first one to sort of demonstrate to do that. All right, any questions on ethers? So just to be clear, for ethers, you need to know the functional group. You need to know the common way of naming an ether. So again, if you had something like this, you again would need to be able to go to the oxygen and go to the right. We have a methyl group. To the left, we have a 3-carbon group, which would be a propyl. And again, alphabetical M before that would be methyl, propyl, and then you just put ether at the end of it. So you do need to be able to, again, recognize an ether by its functional group, be able to kind of name it with its common name, and you do need to know the properties in terms of boiling points. It falls obviously below alcohols, but above alkanes. Any questions on that? And probably that is used as a general anesthetic, right? So these are alkyl halides, and I'm not going to talk too much about these. We sort of did with alkanes when we were doing alkanes. Really what an alkyl halide is an alkane that has a halogen at the end. So halogen, right? These are all our group 7s. They're called an alkyl halide because they contain a carbon group, which is what an alkyl group is called. Halide because they contain a halogen, right? Which is group 7. You could classify these just like anything else as a primary, secondary, tertiary alkyl halide. Works the same way. The carbon that's attached to the halogen, this guy is attached to 1 carbon, so it's a primary. The carbon attached to the halogen is attached to 1 and 2 carbons. and that would be a secondary alkyl halide. And much like everything else here, this carbon is attached to 1, 2, and 3 carbons, which would make it a tertiary alkyl halide. So you could kind of number alkyl halides, which again is just a fancy word for an alkane that has a halogen in place of a hydrogen. They do typically contain polar bonds because we basically have a highly electronegative atom, right, in group 7, attached to a carbon, so you get this separation of charge. And it does have increased boiling points with the size of the alkyl halide, so the bigger it gets, the higher the boiling point typically gets. So here's sort of these are all alkyl halides. Again, if we were to name this would be chloroethane. This would be 1-chloropropane, just like we did when we talked about it with alkanes, 1-bromopropane. And again, the size here is increasing as we go to the right. And we see that the boiling point also increases as we go to the right as well. So with alkyl halides, the boiling points between each of them increases as the size gets larger. A couple of reasons: we have that polar bond here. We also remember this part, which is technically nonpolar, also increases sort of the strength as this part gets bigger as well. All right. We've already named those. We already talked about naming those in the alkane chapter. So again, I'm not going to go too much into that. So then we're off to the next group, which is a thiol. So this guy here is another organic compound, which are known as thiols. And the thiol functional group is a sulfur-containing group, usually SH. And this is its functional group. The SH bond is kind of similar to the OH bond that we see sort of in alcohols. And it is similar in terms of electronegativity, right? If you look on the periodic table, they're very close to each other, S and O. So they have very similar properties as alcohols, just like in an alcohol that looks just like this, which is ethanol. This thiol is pretty identical. It has 4 electron pairs and 2 bonds, which is going to be our V-shaped. And same thing with our alcohol, it has the exact same geometry there at the end. It's got 4 electron pairs and 2 bonds, also going to be bent or V-shaped. We'll have sort of that V look at the end. Now, in terms of thiols, though, because they do not contain an oxygen-hydrogen bond, they typically will have a lower boiling point than alcohols because they lack, again, the big key here for boiling points and stuff like that is the ability of the hydrogen bond. So although it does have that SH group, remember to hydrogen bond, it needs to be a bond between hydrogen, oxygen, nitrogen, or fluorine to be able to hydrogen bond. So in an alcohol, we have that bond, but in a thiol, we don't. So again, even though it has a hydrogen, it doesn't have one of those oxygen, nitrogens, or fluorines attached to it. So again, technically not going to be able to do as a hydrogen bond like we do see in alcohols. So what that means is, as we can see on the bottom, the alcohol is still the champ here in terms of boiling points. It is higher than a thiol. By the way, this is the way you name it. This is 2 carbons, which is based off of ethane, and this is a thiol. So that is how we get ethane thiol. The good news is you don't have to name thiols, but you do need to know the functional group for a thiol, which is that SH group, and you do need to be able to recognize something as a thiol. We will not be doing any type of naming of thiols, so you don't have to worry about it. Now, in terms of not worrying about the actual naming of thiols, which is good, because it does contain sulfur. If you've ever smelled sulfur before, it is not a pleasant smell. But these thiols do go through two reactions that you do need to be aware of. So the first one is an oxidation reaction. And if we take these two thiols, I'm just going to draw them out side by side. So we basically have two of these guys. And it is going to go through an oxidation reaction. And this oxidation reaction is the exact same type of oxidation reaction we talked about with our alcohols. It is going to be the loss of H2. And the H2 comes from a hydrogen from one and the hydrogen from the other. So these two hydrogens are going to come off and produce H2. Now, what essentially happens at this point is once it loses its two hydrogens, you essentially just squish together whatever's left over. So what you would do is you would start on the left-hand side and just write what's there, CH3, CH2, we have a sulfur. You obviously would take out the middle section here and then connect over to the next sulfur and what's left there. Now, this bond where we end up with two sulfurs that's bonded together, this is what is sometimes referred to as a disulfide bond or bridge. And disulfide bonds or bridges is an important sort of bond that occurs when we do get these two sort of thiol groups together. We will see this again when we talk about amino acids. There's an amino acid that contains this SH group in it. And part of sort of proteins and amino acids, sort of how they come together, you form a lot of disulfide bonds or bridges that occur between different amino acids, and obviously causes some different sort of effects to occur. So you could put together any two sulfurs like this. They don't have to be the same sulfur. So for example, if we had this guy here, actually we'll draw it out here. And we added it to, say, another sulfur. Again, the same thing's going to happen. We're going to, if we do an oxidation reaction, we're going to take an H from one, an H from another. That's going to give us H2. And then we're simply just going to go left to right and draw them together, where the connection is always going to be the two sulfurs. So that's an important aspect of this. The connection always going to be these two sulfurs here. So basically we drew that, we drew that, we drew that, we skip what's in the box, and we continue on this way. So we drew the sulfur and we have just this guy that's left. You know? So again, if you take two thiols together, do an oxidation reaction, we're going to take out the H2, squeeze everybody together. Obviously, you could do the opposite of that, like we talked about. The opposite of an oxidation reaction is a reduction reaction. And that's essentially what that stands for. Like I showed you before, that means a reduction reaction. And reduction, remember, definition of reduction is really adding H2. So essentially to this, we're going to add H2. And how this comes apart is it will always come apart between the two sulfurs, because when we put it together, we put the two sulfurs together. So if we're going to break it apart, we would break it apart at the two sulfurs. And essentially one guy will get an H and the other guy will get an H. And again, nothing changes. So you just draw it exactly the way it looks. Now, here's where I broke it apart. So I'm going to put one hydrogen there. I'll just say that hydrogen, for example. I'll box it so you can have a reference. And then the other hydrogen, I'll put a circle around it, will go on the other side, and the other hydrogen that I put on there. So the oxidation reaction of two thiols is putting it together to make a disulfide bond. The reduction is the opposite reaction where we break it apart and put a hydrogen back on to each of them. So for thiols, you need to know, like I said, the functional group. You need to be able to recognize something as a thiol. You do not need to name a thiol, but you do need to know these two reactions. So you do need to know the oxidation reaction where we put them together and be able to draw the product. And you need to know how to draw the product of the reduction reaction when we break it apart. Any question on that? Okay. And like I said before, and we'll see this a little bit down the road as well, a lot of times in amino acids, there is an amino acid that does contain this thiol, and that's where we get a lot of in proteins. You'll see sometimes a lot of these disulfide bonds that occur, again, between these sort of thiol groups on different amino acids. And that causes things to happen, like some of these proteins to kind of fold up on each other, depending on where those disulfide bonds or bridges basically occur. All right, any questions on thiols or what you need to know from thiols? Okay, the next thing we're going to talk about then are two more important organic groups. These are aldehydes and ketones. So the aldehyde and the ketone, they both contain a carbonyl group, which is that carbon-oxygen double bond. And for our aldehyde, which is over here, the functional group of an aldehyde is what we saw earlier when we were talking about the alcohols, the carbon-oxygen double bond with the hydrogen. So this again is our functional group. While this guy over here is a ketone, and again, a ketone's functional group is 3 carbons in a row, where that center carbon has the carbon-oxygen double bond, and this would be the functional group for a ketone. Now, a couple of differences here between these two functional groups is in an aldehyde, there's one very important. So hydrogen has to always be at the end, never be in the middle, too many bonds, electrons. So we have a group. The functional group will be one end of the molecule or the other end of the molecule. Middle. Different is carbon double bond. Carbon, which means hydrogen double bond, will never ever find itself at the end because you'll always need that extra carbon on each side. So the aldehyde will always be at the end. The carbon-oxygen double bond from the ketone will never be at the end because of just the setup of how it goes. The carbon-oxygen double bond, as we will see, is a polar bond, with the oxygen being more negative, the carbon being more positive based on electronegativity difference. So it does allow these guys to interact with certain types of molecules through that carbon-oxygen double bond. So because of the carbon-oxygen double bond, the geometry that we typically get is that trigonal planar geometry. That again is 3 electron pairs and 2 bonds. Remember, double bonds and triple bonds count as only 1 when we're doing geometry. So 1, 2, and 3 electron pairs, and also 3 bonds, which is our 120 degrees, our sort of triangle geometry that we see. And it is based on that polar group where, again, the carbon is more positive and our oxygen is more negative. And that's important because, again, if you had something, for example, perhaps like water, which is positive and negative, it gives something like water and this guy sort of the ability to actually hydrogen bond with each other. So it gives some of these guys some solubility with something like water because it has that ability to hydrogen bond. So let's talk about how we name these guys. Just like everything else here, we're going to look for the longest continuous carbon chain. It obviously does need to contain our aldehyde functional group. So since we see our aldehyde functional group here, we drop the E and we put Al at the end of it for our aldehyde. So this again has 1, 2, 3, and 4 carbons, which again, as you can see here, is based off of butane. So butane becomes, as you see there, butanal, Al. Now, as we just talked about, this group is always at the end, which means unlike a alcohol or a double bond or a triple bond, you do not need to give the number where you find that group, that carbon-oxygen double bond, because it's an aldehyde, it should always be at the end. But the important part is, because that is the important group here, it does get the priority in terms of the numbering. So you do want to number whichever way will give the carbon hydrogen the smaller number, which obviously will be 1 no matter what. But since the group's over here, we would want to number right to left. So this would be 1, 2, 3, and 4. And that's important for the group that's attached here, which is a methyl group. And that would be at carbon number 3 based on that numbering. So this would be 3-methyl butanal, Al. And that would be good not to miss the other guy that's down here, which is where we get our other methyl group there. Everything just blended there for a second. All right, let's try that again. So we do have this guy at carbon number 2. So as the name shows, this is 2,3-dimethyl butanal. Again, if you didn't miss that second group that was on the bottom. So again, aldehydes gets the Al at the end. The group will always be at the end of the molecule, which means, again, you do not need to number where the carbon-oxygen double bond is, but that is always going to be carbon number 1 in terms of numbering where all the other groups are attached. Now, some aldehydes have sort of common names. So, for example, that's formaldehyde, that's acetaldehyde, and benzoaldehyde because it has a benzene ring. But if we want to IUPAC this guy, again, we see our functional group here. It has 1 carbon. 1 carbon is based off of methane. We're going to drop that E and make it methanal, Al. Again, no need for numbering of the group because it's carbon number 1. Over here, we see our functional group. It has 1 carbon and 2 carbons. That is based off of ethane. Dropping that E, gonna make us ethanal, Al, as the name for this guy. So these again would be the more IUPAC way of naming. These again are the more common way of naming. So you should be familiar as formaldehyde is the same as methanol and stuff like that. So that's one that comes across a lot. People still use formaldehyde a lot in terms of naming and obviously the name of it. Again, this guy here has the benzene ring, which is where this part of the name comes from. And then this part obviously is because it is a aldehyde group that's attached. So let's talk about how we name ketones. Same deal. We're going to go with the longest continuous carbon chain. Again, in this case, we do want to make sure that that longest continuous carbon chain has the carbon-oxygen double bond attached. So here, if we number it, we are numbered the carbons, how many we got? 1, 2, 3, 4, 5 carbons. Again, based off of pentane. We're going to drop that last one and put the ONE at the end of it. And that is going to be pentanone. Now, unlike an aldehyde, because the ketone will pretty much never be at the end, you do need to give the location of where we find that carbon-oxygen double bond. So we do need that location. Starting around 4 carbons or more is typically where you need to put the location in. And we do want to give it the smallest number. So obviously going right to left to right, like they did here, would give us a 2 for that. If we went the other way, 1, 2, 3, 4. Three. So if we put all that together, that gets us 3-methyl 2-pentanone as the correct name here for that guy. Any questions on the ketone name? Now you could have a cyclic type of guy. So if we look at something like this, just this part of it, you may not be able to recognize it, but just to draw it in so you can see it, that's a carbon, that's a carbon, and that's a carbon. That's essentially a 3-carbon run, where in the middle we have a carbon-oxygen double bond. So this is a ketone because of that, and it just happens to be part of a ring structure. And you would do the exact same things we did with everything else with our ketones. It would be based off of cyclohexane because it's 6 carbons in a ring. We drop the E and put ONE. And in a ring structure, although I kind of butchered it here, I'll just put it down here. Where that carbon-oxygen double bond is always going to be carbon number 1. So we would want to number whichever way gives our other groups sort of the smaller numbers. Here we have an ethyl group. Here we have a methyl group. And putting those together in a way where we give everybody the smaller number gives us 3-ethyl 4-methyl cyclohexanone, and that would be numbering clockwise. That gives us groups at 3 and 4. Again, if you went counterclockwise, you would have 1, 2, 3, 4, 5, and 6. That would give you groups at 4 and 5. Again, going to be a larger number. So the smaller number based on the groups would be numbering in this direction. And again, alphabetical like normal. So 3-ethyl, 4-methyl, cyclohexanone. Again, it is a ketone in this case. Any question on how we get to that name? So just like our aldehydes, our ketones, some of them do have sort of common names. Like this is acetone. Obviously, this guy's got a couple of benzene rings on it. But again, if we were to look at this guy and name it with our IUPAC way, we have 1, 2, and 3 carbons. 3 carbons is based off of propane. Dropping that E because it's a ketone, propanone. And technically, you could call it 2-propanone, even though there's only really one place it could be is on that carbon because you need the 3 carbons in a row. So some people may leave the 2 off of that one, just call it propanone, or you could call it 2-propanone. but in reality, there's really no place other than the second carbon in this particular guy here for that to be. All right, so we went through some examples here. So why don't you try some, see what you end up with. So take a couple of minutes here and name each of these. And then we'll talk about it. All right, so let us take a look and see. Um, so again, first thing you want to kind of recognize, this is again the functional group here. And that is the functional group again for an aldehyde, which is those guys that end in Al. So longest carbon chain here that contains that 1, 2, 3, 4, and 5. So that's based off of pentane, and it becomes penta, now Al. Again, no need to number this because it's always going to be carbon number 1 in that case. Any questions on that? Second one here, also we see the same functional group right there, which is our aldehyde. We want the longest carbon chain that contains it. 1, 2, 3. So a lot of people sort of count. Yeah. The location guy is carbon number 1. That's going to be carbon 2. So the carbon 3 is that 3 group. So be propanal. Any questions on that one? And lastly, here on the bottom, we have a 3 carbon run with the carbon oxygen in the middle. That is a ketone. So remember, ketones end in ONE. And what we want to do is count the carbons. So that is 1, that is 2, that is 3, and that is 4. 4 is based off of butane. So butane becomes butanone. And we do need to give the location here of this carbon oxygen double bond. we want to give it the smallest number. So left to right, it would be at carbon number 3. Right to left, it would be at carbon number 2. So ketone would be the name here of our ketone. Any questions on that there? Okay. We got a couple more. So why don't you, actually, let's go to this one. Why don't we draw them? So draw the structures for each of these and see what you come up with. Let me do that one first. Okay, so let's see how we're doing here. So let's just get some stuff out of my way so I can actually see what it says. So just like usual, when we do have the name and we want to work backwards, we want to work backwards on it. So we're going to start with the back part of the name. First off, the Al tells us that it's an aldehyde. And the penta part tells us that there should be 5 carbons. So that's really where you want to start. 1, 2, 3, 4, 5 carbons. Because it's an aldehyde group, it will have this as its functional group. And as we talked about, it does need to be at the end. So since you're drawing it, you could put it on the left-hand side, you could put it on the right-hand side, I'm going to choose to put it over here on the right-hand side. And the consequence of putting it on the right-hand side means that this guy right here is going to be carbon number 1. And that's important for what's left up here. And that means that carbon number 4, we have a methyl group. So since this is going to be carbon 1 on the right, 2, 3, 4, that is one group. And if you did the aldehyde on the end, you just flip this whole thing around. Just like everything we do, it's going to be hydrogen to make sure that this guy at the end we need carbon has 4 bonds. This carbon coming in, which means you need 1 hydrogen, has 2 bonds coming in, means he needs 2 hydrogen. This carbon has 2 bonds coming in, which means 2 hydrogen, 4 bonds, so it does not need any hydrogens added to it. And just to get rid of the 1 there so it doesn't look like anything, that would be our 4-methyl pentanal. Any questions on how we dissected it? We do want to do the same thing with the next one. So going backwards, we see the same Al, which tells us again it's an aldehyde. This case, though, we see propane, basically. Propane means only 3 carbons in this case. So again, that's what you want to start with. 1, 2, and 3 takes care of that. Again, because it's the aldehyde group that's going to go at the end, I'm going to choose to put it on the right-hand side, but you could put it on the left, but it does have to go at the end. And because, again, I did that, where I made the carbon-oxygen double bond is going to be carbon number 1, which means that carbon number 2 and 3, there is a chlorine group. So this would be carbon number 2, and this would be carbon number 3 in this case. Again, because carbon number 1. Just for I'll deal with it over there. So 2 carbon, the guy on the 2. I'm good for this, and one is the next carbon 2. Now we're on the 2 versions right there. Let's take care of it here. Because those are right in this case. That means this carbon 2, 3, 4. We have group 1, 3, on top of that. Now we're going to starting the 3. That means not the end. 3. So our ketone would look something. So remember that when you are working backwards in the name, you want to look at the name. The name has a lot of hints as to how to draw it. Start with the carbons, add the functional groups, add the alkyl groups, add the hydrogens at the end. Any questions on how to draw those guys? I think we did those. So, all right. So let's talk about some of these properties of aldehydes and ketones. Aldehydes and ketones will have a higher boiling point than alkanes or hydrocarbons. Again, this is basically our alkane, which we'll be using that dispersion force, which is that weak force. This is our aldehyde group, which again, although it cannot hydrogen bond itself, does have a polar group here. So it can do a little dipole-dipole sort of interaction. So it does have typically a higher boiling point than what we see in a similar size alkane. But our ketones will have a lower boiling point than our alcohols. Again, our alcohol is still the winner here because of its ability to hydrogen bond. So because of that OH group that we find in an alcohol and that ability to hydrogen bond because of it, our alcohol still here has the higher boiling point because of our ketones' lack of ability to do that hydrogen bonding. Now, they're also soluble in water, so aldehydes and ketones are soluble in organic solvents, but they're also soluble in water as well, with about 6 carbons or less. And it's for the same reasons we talked about earlier. Although they themselves cannot hydrogen bond, because they contain this group here, both the aldehyde does and the ketone. When something like water does come along, which is also polar, it is able to hydrogen bond with water. And again, if the ketone or aldehyde is not very large, usually around the 6 or less cutoff for most organic things that have the ability to interact with water is sort of where you cut it off. It typically will be soluble in water. As you go above the 6 carbons, again, you're essentially just building out the non-polar side of the molecule. It's getting larger and larger, and it again interferes with the ability or the effectiveness of that carbon oxygen double bond to interact with water. So the solubility pretty much becomes insoluble above 6 carbons. All right, here is some aldehydes and ketones of interest. We have cinnamon aldehyde for like cinnamon. We have vanilla. Again, these are aldehydes. Here's our aldehyde group here. That's the way the aldehyde group is sometimes written, CHO. And again, that represents this group. And again, we see the aldehyde group here, sort of written that way. Most of the time, people will actually draw out that group, but sometimes kind of a condensed or shorthand, you'll sometimes see it written like that as well. Here's some other ones, citronella. Also, again, you see your aldehyde group in each of those. So let's talk about the actual reactions that occur between aldehydes and also perhaps with ketones, if they do. Now, aldehydes will go through an oxidation reaction, and this oxidation reaction, as we go from here to here, is actually the gaining of oxygen definition. So if you look at our aldehyde over here, and you look at what happens to it after it goes through oxidation, a very simplified version of what happens is we essentially inserted an oxygen here. There's a lot more to it that actually does occur, but basically the major difference is you draw it exactly the same and you just slap an oxygen right there, as you can see on the other side. There's a lot of things that happen to get that oxygen in that spot, which is outside of our class in terms of scope, but that's essentially the difference that occurs. Again, that O there means oxidation, and essentially we go from our aldehyde to a carboxylic acid having that functional group that looks like this. Sometimes that we were in short. You may also remember this primary alcohol. This is the removal of an H and then double bond to our aldehyde. So a primary, you get aldehyde, which is really more from the alcohol. If you further the aldehyde, you will get a carboxylic acid. And by the way, the reverse reaction in each of these, we could take carboxylic acid and reduce it to an aldehyde and get our primary alcohol back. So again, it's the opposites of each other. Oxidation and reduction happen together. So to do this reaction, sometimes you'll see some type of reducing agent here, like potassium dichromate, again, just here to facilitate the reaction happening, not really involved. The only difference as you go from our butanol to our butanoic acid, which is a carboxylic acid, is if you circle it here, that's CH3, exactly the same as you see here. That's CH2, exactly the same as you see here. That's CH2, exactly the same as you see here. That carbon is exactly the same as you see here. That double bonded oxygen did not change, exactly the same. The only difference is we insert And this would be our oxidation reaction going from an aldehyde on the left to a carboxylic acid on the right. Any questions on that? Now, when we look at ketones, and if we try to do an oxidation of a ketone, we actually do run into a little bit of a problem. The aldehyde, as we saw on the previous page, has that hydrogen attached to the carbon. That's in that carbon-oxygen double bond. But when we come to our ketone, we actually are missing that hydrogen. And because we're missing that hydrogen, we essentially have no carbon-hydrogen bond. And although we don't get into how this whole process occurs with the aldehyde, that carbon-hydrogen bond is really important in the process of actually making the reaction. So if you try to oxidize a ketone, you get no reaction. So this is a really good way to determine whether or not you are starting with an aldehyde or a ketone. You would run them both through an oxidation reaction. And if you did see a product of that reaction, the aldehyde would make the carboxylic acid. While again, if you tried to oxidize that ketone, you would get no reaction. And there's two sort of tests that you could run to verify whether or not you started with an aldehyde or you started with a ketone. And one is what is known as a Tollens test. And they will show the oxidation of the carboxylic acid, which means if you run either one of those tests, and we'll see what they look like in just a second, but if you run either one of those tests and it's positive, what that means is you had an aldehyde, and this reaction occurred, not the one we see here, but this reaction right here occurred where we basically went from an aldehyde to a carboxylic acid. If you run the Tollens test or the Benedict's test and it is a failure, it did not work, that would tell you did not have an aldehyde. And in the lab that you typically would do with this one, the other option would have been, it would have had to be a ketone. So you could kind of use this process where an aldehyde will go through oxidation, but a ketone won't, to determine if you started with an aldehyde or you started with a ketone. So let's take a look at what those tests sort of look like, I think. So the Tollens test selectively oxidizes only an aldehyde, and we use silver, which is what is basically being what's happening here. And the silver is actually going from a charge of +1 to a charge of 0. It sort of makes solid silver, if you will. And that solid silver, as you'll see in a much better picture, will kind of turn the test tube a mirror type color, the silver color. And that would be a positive test for an aldehyde. Now, if you did the same test with a ketone, you would not see that silver color basically occur. You would, and because you would not see it occur, it would be negative, and you know it would be a ketone. So when we look at this and it goes through oxidation, which is essentially what's happening here, the only thing that changes is right there. So you can see everything's the same from what we started with. We have the OH group, we have our 6-member ring, exactly the same. We have our carbon that's the same. This would be a positive test for an aldehyde. This test does not work for a ketone. So if you get a negative test and your choice is either an aldehyde or a ketone, then you have a ketone. Here's what that test actually looks like when you run it. This is the Tollens test. Again, the silver goes from +1 to 0, which means it gets reduced. And it makes this really silver color, which is sometimes what's referred to as like the mirrored sort of test. And that is what happens when you do the Tollens test. I think in the lab, when you physically would do this experiment or when you see the experiment done, they actually run the Benedict's test. And the Benedict's test is one that I think we were still on campus and you did this experiment, I think. It's the one with the dialysis bag where you sort of test things, what's in the bag, what's not in the bag, I think. And the Benedict's test uses copper. And what happens with the copper is it goes from copper with a +2 charge, which is this blue color, to copper with a +1 charge, which is, I want to say it's red. And in reality, it's kind of like a gross looking orangey color sometimes. But that is sort of a positive test. Again, the copper is getting reduced while our aldehyde would be getting oxidized. So the Benedict's test is also a test that you use to see the oxidation of a aldehyde into a carboxylic acid. If you run the Benedict's test on a ketone, it will not work. And again, that's a way you could distinguish between them. Any questions on those two tests, which I think might be the next experiment? So just to make sure everybody understands, if we take this guy here, and I do an oxidation of this guy again, and if I have, say, this guy, and I do an oxidation of this guy. So let's take a look at what will happen here. First off, we see this is a aldehyde. And again, an aldehyde will oxidize to a carboxylic. And when we go to draw it, the only thing that changes when we do this is at the very end. And it is, so you copy it one here. Going through it and would this question out. So joint effects don't do anything too fancy or crazy. It pretty much it also should then tell us that we have no wings because they will not. So either result for this negative for this guy, and we will learn from those tests that the positive one would be our aldehyde, the negative one would be our ketone in most often case if you're comparing the two. Any questions on that? That, believe it or not, is the end of chapter 12. Any questions on anything we talked about? So as we talked about in the first lecture, again, the exam is not going to be next week. It's going to be moved to the 11th, which should be a week from Monday, I believe. And we will continue lecturing next Monday. And we're almost there. We got 2 more weeks and like 4 chapters. So that seems like fun. Any questions on anything I can help you with? Okay, well, thank you very much for coming and staying. I appreciate it. Have a good night and a good weekend. And I'll see everybody next week.